Okay, so hello guys. In this video, we are gonna January. Yeah, so this date over here, it's just yesterday. Today is 21st January. So I'm pretty close at any of these problems, and I wanna solve it together with all of you guys. Try to solve all 20 problems. Let's see. We will try. I don't know. Okay, let's go with the first one. We also have the answers here, and that's a good thing. So let's go with the first one first. The first one should be pretty easy, right? Okay. So there's a second viewer. I think I would appreciate if you also engage with the problem. Okay. So yeah. So now we have integral from minus pi to pi. Oh, could we use Wallis formula for the first one? Let's see. I haven't tried it, but I don't think it will be that hard for soon. I don't think we need to use Wallis product. It should be easier, you know? Okay. So what you can probably do for soon, like maybe if we write the sine thing as sine square x to the power this is 1006, which is 20, let me write 1012. So this is 2024, and then cos 2026 with the sine x dx, right? So what I just did was I broke sine to the power 2025 into sine to the power 2024 and the sine. So I guess you know what I'm gonna do next now. So what I will just do is write this in terms of cos x. Yeah. And then, yeah, now we'll just do this substitution that we do. Yeah. Okay, now if I substitute y as cos x, right? So if I substitute y as cos x, what will happen? I will have dy as minus sine x dx. So this will just be, now this will go from cos of, okay, so this will go from -1 to, so this will go from 1 actually, or no, this will go from -1 to 1, which definitely seems to be a problem. Oh wait, I don't even need to do this integral. This integral is actually very easy. You know why? This integral is actually so easy. The reason is, notice that if I have f of x equals to sine to the power 2025x cos to the power 2026x, yeah, so because there was same limit, so we know the integral will be 0, right? And also, like, to explain that in a different way, what I can also do is, if I find f of minus x, this is just minus, yeah, exactly, odd function, right? Not even, odd function, right? So because this is odd function, so we know that if something is an odd function, okay, because f(x) is, yeah, no, I understand, yeah. Okay, because this is odd function, we know that if it's symmetric domain, the integral of odd function is 0. So because of that, so here we have a equals to pi, right? So that's why the integral is 0. This was an easy one actually. Okay, so we are done with the first problem. Okay, so let's just check the answer just in case. So yeah, the answer is 0. Okay, let's go with next problem. Okay, we have 4 viewers now. I definitely recommend all the viewers to engage and help me, because I also haven't tried these problems till now. This is my first time trying these problems, and I think if you guys can share your ideas, it will be helpful for me. Best. So this problem. Saurabh Astana. Okay, good, Saurabh. Okay, Saurabh. Now for this one, we have e to the power 2026 e to the power x with e to the power x dx. So what's my thought in it? What's your thought in it? I think this one shouldn't be that hard. I think if you just let the first term as y, then you will somehow have this expression in the differential, and then I think it will just simplify after that. So let's do that. E to the power 2026 e to the power x, and then dy will be e to the power 2026 e to the power x time 2026 e to the power x, right? So yeah, just like I said, and then dx. Over here, dy by 2026 is just e to the power 2026 e to the power x with e to the power x dx, right? So that means this expression is just dy by 2026. So that is just 1 over 2026 y plus c. And in this case, y is e to the power 2026 e to the power x plus c. So it turns out this wasn't really a hard problem. Yeah, this was just substitution. So let's take the answer. 1 over 2026 e to the power 2020 e to the power x. Yeah, exactly what we got, right? Yeah, this wasn't a hard problem. Let's go with the next one. I think I will need your help in the next problem. Okay, so this one seems like a good problem, guys. There's that thing, you know, the greatest integer function. I guess you guys know about that function, right? The greatest integer function. So basically the greatest integer function, let's say if I have 3.15, this rounds down to 3. Similarly, when if I have 3.67, this will still be 3. So basically greatest integer function is greatest integer less than x. Okay, so let's say if you could that also be a fractional part function. Sorry, fractional part function is something is written like this. So this is fractional part of x. Yeah, the curly. Yeah, so we can also write fractional part as x. Sorry, the greatest integer as x minus the fractional part. We can also write it like this. Yeah. Oh yes. Oh, I see what you're saying. The outside curly brace definitely is fractional part. This is very interesting. Okay, I already have answer here. I'm sorry. And then this is yeah, exactly what you're saying is right. So this bracket is greatest integer function, and the outside braces is the fractional part. So let's see how we can do this. Yeah. So okay, so let's see. So over here, so first of all, what I can do is, because there's this fractional part function, right? So I can essentially, so for let's say, okay, I can essentially write this integral as integral going from n to n plus 1, right? And then this n going from 0 to 2025, right? And then fractional part, I will tell you why I did this, over 3 and then dx. So what I did was I wrote the entire integral as sum of multiple integrals, integral from 0 to 1 plus integral from 1 to 2 plus integral from 2 to 3 plus integral from 3 to 4 of 2026. And the reason I wrote it like this is that, so now it's because I wrote it like this. Notice that, so in this domain, when our integral is going from n to n plus 1, right? If I take the fractional part, so let's say if it goes from 5 to 6. So whenever x is, let's say 5 or 5.1 or 5.2 or 5.9, for all these numbers, the greatest integer function will just be 5, right? So that means in this domain of integration, our greatest integer function of x will just be n. So this will just be n over 3. Do you guys get the idea? So this is actually a really helpful idea. Whenever you have greatest integer function, you actually break the integral as multiple integrals going between like some lower integer to upper integer, and you write it as a sum. This is a very popular idea. Okay, so now you have this. Now what's next, right? Okay, so now what's next? So we need to think about it. Over here, okay, so now we have, okay, so what I can do next, I need to think about it as well, right? Okay, so let's see. So we have this n over 3, right? So whenever n is in between, let's say 0 to 3, when n is let's say 0, 1, 2, or 3, right? So our fractional part of n over 3 will just be n over 3 itself, right? Okay, not for 3. When it's 1, 0, 1, or 2, the fractional part will just be n over 3 itself, because it has not exceeded because this thing is still less than 1, right? So now when n is, let's say 3 or 4 or 5 up to 5, in that case our n over 3 will be n over 3 minus 1. You see why? Because like whenever like I have 4 over 3, that's 1 plus 1 over 3, right? And then fractional part will just be the 1 over 3, so I have to do n over 3 minus 1. Similarly, for n equals to 6, 7, 8, the fractional part of n over 3 will be n over 3 minus 2, right? And I think you see why. Because like for 7 over 3, this is just 2 plus 1 over 3, so this is 2.333. So the fractional part will just be 0.333, right? So that's why I'm doing it. So now we have some idea how to proceed ahead, right? So what we are gonna do is, so okay. Also one thing, guys, I just noticed is that this thing is actually a constant, right? So I can just bring that out of the integral. So I just saw that. Okay, if I just bring that out of the integral, so what I have is just integral of 1 dx, which is just x from n to n plus 1, and this is just 1, right? So sum from n equals to 0 to 2025 of fractional part of n over 3, because that thing is just 1. Okay, I think now it should be easy to do, right? Okay, I think now it's easy to do because like because we know that like for whatever are the fractional part for 0, 1, or 2, it will be same for 3, 4, 5. It will be same for 6, 7, and 8, right? So in all these cases, the fractional part will just be 0, 1/3, 2/3. Over here also, fractional part will be 0, 1/3, 2/3. Over here as well, the fractional part will be 0, 1/3, 2/3, right? So up to so we know that 2019 is a multiple of 3, right? Yeah, so 2019, 2020, 2021, so they will all also have fractional part 0, 1/3, 2/3. And then 2022, 2023, 2024, they will also have 0, 1/3, 2/3. And then 2025, this one will have 0, right? Okay, so now let's see how many sets are there. So up to 2022, okay, so 2022 minus 0 divided by 3, so this is 3, 6, 18, 22, 3, 7, 21, 4. Okay, because this is 644, so we add 1. So there are 675 such sets over here, right? And then each set contributes just 1 to it. Like this whole thing, this if we take the sum, that sum is just 1, right? This sum is just 1, right? So everything just contributes 1, and there are 675 sets. So That's and the last thing just contributes 0, so this sum should be 675, and that is the answer, guys. Yeah, okay, so let's see if that's the answer or not. Yeah, that's the answer. So the thing was to first of all change the greatest integer function into a sum, and then just do the integral, and then see how you can actually see that the values, the set of values are repeating, and then use that to get the answer. So yeah, it took us some time, but we did it. Let's go to next problem. Did you guys understand it? Is there anything that I need to explain? Because I took a lot of time. Is it good? Like there are five of you. Do you think this is understandable? Yeah, give me some response, guys, and I will proceed ahead. Probably I should. Okay. Yeah. Okay. Good. Sarabastala. Good. Let's go ahead. Yeah. Let's do this problem. Let's do this problem, guys. Let's not see the answer. Let's do this problem. Let's do this problem. Yeah. Okay. So guys, give me some idea how to do this problem. I have no idea. Okay, guys. Give me some idea. Okay. So we have integral from -1 to 1, right? And there are 26 such things. Okay, first of all, let's see the even oddness of this thing, okay? So let's say if I plug in -x, what do I get? So, okay, so let's say if there's just two of them, right? And if I plug in -x, I have -x plus modulus of -x, right? So this is -x plus x, and that is just 0, right? Okay, so if I have three of them, if I have, let's say, three of it, okay, if I plug in -x, so this will be -x plus -x plus -x, right? So this is -x plus -x plus x. So this is -x plus, this is just 0. This is modulus of -x, which is x, right? And you might similarly argue that if I have another like -x in there, and this whole thing is just x, right? And this whole thing was just x. So if I had like another -x over there, it would have been 0 again, right? So that means if there are even number of them, then it's just 0. If there are odd number of them, then it's just x. It's modulus x, actually. Right? Yeah, it's just modulus x. So over here, just a sec. Wait. I was assuming x was positive in this case, right? Wait. The way I did calculations, yeah, I was assuming x was positive number. I was assuming x is positive number, right? So if x is a positive number, then like, yeah. So if x is a positive number, then I can definitely say that the modulus of -x is x. Yeah, so for x being positive, f of -x will be 0 if there are even number of the x's, and it will just be x if there are odd number of x's, okay? So yeah, so now what do we learn from that? What do we learn from that? Yeah, so basically what we learn from is that, like, because there are even number of them, right? So the integral from -1 to 0 of this whole thing, should just be 0, because for these negative numbers, like I just showed that this function is just 0. Yeah, so for -1 to 0, this is just 0. So it looks like I only need to do it for positive numbers, right? So I only need to do it for positive numbers from 0 to 1. And in that case, for positive numbers, all the modulus, like, it's just same as not having modulus, yeah? Because for positive numbers, it doesn't even matter, like, the modulus is there or not. So that means I will have 2026 axis dx, right? And then, so that is just 2026. So that's what I think answer is. It was just too easy. Well, let's see if that's the answer or not. 2026. No, it's not. It's 1013. Oh, wait. I think I know why. I think I know why it's 1013. I just did a blunder over here. So if I do the integral, this is 2026 x squared by 2 from 0 to 1. So that is 2026 over 2, and that is 1013. Okay, so we did it, guys. This one was a good problem. Yeah. So first of all, I don't know how I did it. This was a really good problem. Okay, so first of all, we saw that for negative numbers it was just 0, and for positive numbers we just added it, and then we did the integral and we got the answer. This was a really good problem, guys. Did you guys this make sense for you guys? Does this make sense? Should we go ahead, or do you guys have, yeah, okay, good, thank you. Okay, let's go ahead. Yeah. Okay, I think for this one, you guys can give your opinions. Let's also have some interactions, right? And then after you give opinions, I will just go with your ideas. Yeah, so what do you think we should do for this problem? Okay, I'll just wait like 30 seconds if you guys wanna give any opinion, something like that. Otherwise, I will just go with whatever I am thinking. Also, yeah. Also, I need to charge my Apple Pencil. Okay, guys, yeah. I think rationalizing will help. Yeah, okay, let's do it. Let's do that. So if we rationalize, this will just be root x plus 1 plus root x minus 1 by x plus 1 minus x minus 1 dx, right? So that will just be half, and then x plus 1 to the power half. This was actually easy problem, guys. This was very easy. Half, and then x plus 1 to the power 3 over 2 by 3 over 2 plus x minus 1 to the power 3 over 2 by 3 over 2 plus c. So the answer is x plus 1 to the power 3 over 2 by 3 plus x minus 1 to the power 3 over 2 by 3, and then plus c. That's the answer. Thank you, Sarabastala. Let's see the answer. X plus 1 to the power 3 over 2. Yeah, that's the answer, guys. Let's go to the next one. Sarabastala, you should also help me with the next problem. Next problem, yeah, I don't think this one is also too hard, actually. But yeah, I would definitely wait for your opinions before I go ahead, because I also need to charge my Apple Pencil. Yeah, guys, say something and then I will try your ideas. Okay, so what do you guys think I should do for this problem? I'll just go with whatever you guys have in mind. Can you solve one question? I wanna do all these problems first. Maybe I can, like, you can just comment on one of my other videos, and then I will solve it. Okay, like right now we are solving the problems from MIT integration B, so let's go with that. And then you can maybe comment on one of my different videos, and then there I will respond to you if I am able to solve the problem. If I cannot, then yeah, I cannot. Yeah, does that help? Yeah, guys, so what's your thought for this problem? How should I solve it? If you mean like can you solve problem 1, then I already did over here. For the problem 1, we just use the fact that it was odd function. Otherwise, if you want to ask different problem, maybe sometime later. Yeah. Okay, so how should I solve this problem, guys? Sarabastola G. Vardi, I'm sorry if I misread your name. Prasunadikari, what do you guys think for this problem? Just give me some random ideas. Anything is helpful. Guys, anything, like any idea. Like, what about you think? Like, I don't know. What would be your first approach? How would you try to remove that square root, maybe? Or maybe try to simplify this expression? Anything. No idea, guys. Guys, there should be something. There should be something that you want to try. Okay, let. We'll do this later on, like DZ and 764. Right now we are. I guess. Okay, DZ and 764. Right now we are doing MIT integration problem, so I won't go to that. But definitely I will come back to this stat later on. If it's still there, I don't know if it will be there or not. If it's there, I will come back to it and I will try to solve your problems. If I'm able to, and if it's a good problem, I will also make a video. Otherwise, I will probably just respond in this chat itself somewhere. Okay. Not too familiar with hyperbolic trick, but is it possible to write as some sort of exponential function? Yes, it's also possible to write in terms of exponential function, but I think the approach suggested by Saurabh Bastula is more helpful. If we try to turn it to like hyperbolic cosine square x, then we can cancel the roots. I think that will be more helpful, even though we can also definitely write it as exponential function. Okay, so yeah, let's go with Saurabh Bastula's approach. So we know that like in trigonometry, 1 plus cosine of x is 2 cos square x over 2, right? Is that correct? 1 plus cos 2 theta is 2 cos square theta, yeah. So also similarly in hyperbolic trigonometry, there's this formula, 1 plus cosine of x is equals to 2 cosine of x square of x over 2, right? And see, just like again, I think there are equivalentness to all the formulas. So even for this formula, there's actually an equivalent hyperbolic formula as well. Even though I don't think this is what you might guess. This is -2 sine h square x over 2, right? Yeah, there are formulas. Okay, so now we will use this formula. And if we use that, this becomes 2 cosine h square x over 2 dx, right? And then, so this is just √2 times cosine h x over 2 dx, yeah? That sounds good. Yeah, that sounds good. And now we can just do this. This is just hyperbolic sine of sine h of x over 2 divided by 1 over 2 plus c. So this is 2 hyperbolic sine h of x by 2 plus c, and that is the answer. Yeah, this wasn't too bad actually. So let's see the answer. 2 hyperbolic sine h x over 2. Yeah, that's the answer. Let's go with next problem. Let's go with next problem. We should go a bit fast, I guess, right? Okay. Let's go with problem 7 now. We almost made it to the half. There are just 20 problems. We don't really need to worry a lot. But yeah. Yeah, how will you guys do this problem? I don't think this is actually a hard problem. But let's see, it could be hard. Do you guys know this idea? The fact that a to the power ln of b can be written as b to the power ln of a. Is that even a thing? Yeah, I think the reason is a to the power ln of b is actually e to the power ln of a to the power ln of b, right? So this becomes e to the power ln b ln a. And if I write this as e to the power ln b to the power ln a, so this is just b to the power ln a. So basically a to the power ln b is just b to the power ln a. So I think that's the idea in this problem. Because if you know that, then this is just x to the power ln 2 by x square, right? And I think now this is pretty easy, because now this is just x to the power ln 2 minus 2 dx. And now this is not 1, so I can just use the power rule, ln 2 minus 2 plus 1 by ln 2 minus 1 plus c. So yeah, that's the answer, x to the power ln 2 minus 1 by ln 2 minus 1 plus c. Do you see it, guys? This was actually very interesting problem, right? Let's go to next one. Should I go to next one? Probably, yeah. This was a good problem, right? I think, and this wasn't too hard. Should I go to next problem? Yes, I think yes. Yeah, thank you. Yeah, let's go to next one. And let's take the answer. X to the power ln 2 minus 1 by ln 2 minus 1, yeah. So the next problem is this sum, problem 8. Allah. Okay guys, so think about this problem. How should I approach it? Okay, this problem seems like it's a really good problem, right? Yeah. So do you guys want to do the integral first or sum first? What should we really do? Because over here the modulus of x is less than 1, because it's going from, because it belongs to 0 to half. So we can do infinite sum. Should we do infinite sum first or the integral first? Because we can also swap it. What do you think we should do first? I think we should try both ways. Can you swap the integral and sequence? Yes, if it's absolutely converging, we can swap it. And I think in this case, it definitely is. Okay, guys. So, yeah, let's do the integral first. Okay, let's do the integral first. Okay, as you said. So, if we do integral first, sum from n equals to 2 to infinity. And then this integral is from 0 to half of x to the power n dx. So, sum from n equals 2 to infinity. And then this is x to the power n plus 1 by n plus 1 from 0 to half. So, sum from n equals to 2 to infinity. That is just half to the power n plus 1. I think this one is actually, I don't think I should have swapped it. I don't know, let's see. Minus 0. So this is sum going from 3 to infinity. Wait, let's just write it from 2 to infinity of half to the power n plus 1 by n plus 1. Right? Now what's the formula for summing this thing? We know that if it's, let's say, sum from n equals 2 to infinity of x to the power n, and modulus of x is less than 1, we know that the sum is a by 1 minus r, right? So in this case, a is x squared by 1 minus r is x, right? Now, if we integrate both sides, sum from n equals 2 to infinity is x to the power n plus 1 by n plus 1, right? And in this other side, we have integral of x squared by 1 minus x dx. And specifically, yeah, and I think, wait, let me write this as d. And actually, let me integrate both sides from 0 to x. From 0 to x dx. Okay. And there's reason to do that, because so that this integral on this side will be a definite integral, and that's what we want, right? And the result will still be same, but the other side will have definite integral, and that's a good thing. So now let's do this integral. To do this integral, what I can do is, I can first of all introduce a minus 1 and plus 1, 1 minus t dt, right? And then we have integral from 0 to x of t. Did I just make it harder? Well, let's see. I don't know. I don't think it should be that hard. 2 plus 1 by 1 minus 1 over t dt. I don't like the fact that I'm getting log over here. T squared by 2 plus t plus I have ln of 1 minus t by minus 1. 0 to x. So this is x squared by 2 plus x plus, and then actually minus. Actually here it should be minus ln of 1 minus x, and then plus ln of 1, which is 0. So I get this as the answer, and I don't know why I got log over here, because usually I don't think there's log in there, right? Yeah. Wait. So, okay, so did I do it right? So if I just add up t to the power n, this would be a by 1 minus r, right? So t squared by 1 minus t, yeah. And if I want to integrate that, yeah, I think it's probably good. Yeah, because I don't think I have made any mistakes. So, and if I integrate that, oh, wait, over here, I have made a mistake over here, a little mistake. So this should be minus t minus 1, right? Because that's t square minus 1. So this should be okay, so if I divide by 1 minus t, I will have minus t minus 1. Okay, and then that means this is minus t square minus t, yeah, and then minus x square minus x, right? And so I will have minus x square minus x. But then the whole thing is negative. How can it be negative? Bro, it doesn't make sense, and it doesn't make any sense to me. How can it be negative, bro, guys? T square plus 1, t minus 1. It just cannot be negative. Guys. Okay, well, guys, let's say. Even if we did the sum first, should have been the same thing, actually. Yeah. Okay. So we did the integral first, and then half to the power n plus 1 by n plus 1. And again, to do that, we again need the sum thing. We don't really know the formula. Right? Because we don't know the formula. Yeah. I thought there was an easy formula for doing that. Because, like, okay, let's say if I have sum from n equals to 0 to infinity of x to the power n, this is just 1 by 1 minus x, given that modulus of x is less than 1, right? Now if I integrate both sides, so let me write this as t, okay? Yeah, and if I integrate both sides from 0 to x, right, so we have sum from n equals to 0 to infinity of x to the power n plus 1 by n plus 1 as ln of 1 minus t by minus 1 from 0 to x. So this is minus ln of 1 minus x. Yeah, which makes sense. Yeah. Oh, wait. This is actually not a hard thing. This is actually pretty easy. Bro, why I was spending so much time with this, bro? This is a well-known sum, guys. This is just... Well, I'm sorry for being so stupid over here. I'm sorry for spending so much time and being so stupid. Okay, guys. We know that the sum from n equals to 1 to infinity of x to the power n divided by n, this is just minus ln of 1 minus x, right? We know this thing. Yeah? Yeah, we first of all know that x minus x squared by 2 plus x cubed by 3. We know this sum, right? Which is just ln of 1 plus x. And now if we just make x minus x, this whole thing is just, everything is just minus, right? This is ln of 1 minus x. And now if I again multiply minus, this whole thing plus is just minus ln of 1 minus x. So, okay, now we are there. Okay, now I can write this as sum from n equals to 3 to infinity of half to the power n by n, right? So if it was from 1 to infinity, that would have been minus ln of 1 minus half, right? But there are, because the n equals to 1 and n equals to 2 is absent, so we have to subtract that. In n equals to 1, we have half to the power 1 by 1. For n equals to 2, we have half to the power 2 by 2, right? So we subtract those two terms and we get the answer. So now the answer will be minus ln of half minus this is half plus 1/8. So this is ln of 2 minus this is 5/8. So ln of 2 minus 5/8 should be the answer. Still, the answer is negative. How does that make sense though? Because we are just adding positive numbers and we are getting a negative answer. Isn't ln 2 minus 5/8 a negative number? That still doesn't make sense to me. Well, let me calculate ln 2 minus 5/8. Ln 2 minus 5/8. Oh no, that's positive number. Okay, that makes sense. Yeah. Okay, guys, I'm sorry for spending so much time being so stupid, but yeah, we finally did it. Yeah, are you guys there with me? Because we finally did it, guys. I'm sorry for being so stupid. Okay, so this should be the answer. Let's check. ln 2 minus 5/8. Yes, guys, we did it. And this is positive number. I just checked it in calculator. This is positive. Okay. Let's go to next problem, guys. Is anyone there with me? Like, I feel like some of you already left me. Yeah. Okay, let's go to next problem. So, guys, suggest me the approach for this problem. Suggest me a good approach for this problem. And I will go with whatever you guys suggest me. Okay, guys, what do you think we should do for this problem? Yes, integration by parts. That's the correct thing. Yeah, I'm definitely gonna go with what you said. Integration by parts. Okay, so if I do that, yeah, by parts, yeah, exactly, I literal. Okay, if I do that, this will be, we know that integration of u v is u integration of b minus integration of derivative of u integral of v, right? Euler principle, function selection. Yes, exactly. So in this case, I'm gonna select u as x square and then v as sine x. Okay, so this becomes x square, integral of sine x is minus cos x, minus integral derivative of x square is 2x, integral of sine x is minus cos x dx, right? So this is minus x square cos x plus 2 times integral of x cos x dx. Again, I will do the same thing. This is minus x square cos x plus 2 times, yes, again by parts, true. So this is x, integral of cos x is sine x minus integral derivative of x is 1, integral of cos is sine x dx. Okay, so this is minus x square cos x plus 2x sine x, and now this is integral of sine is minus cos, so that will be plus 2 cos x plus c, and that is the answer. This was a very standard problem. Yeah, minus x square cos x plus 2x sine x plus 2 cos x. Let's see, minus x square cos x plus 2x sine x plus 2 cos x. Yeah, exactly, that was correct. Let's go to next problem. We still have a lot of problem, but we made it to half, guys. We made it to half. Yay. Taking cosine. Yeah, exactly. I think those people took cosine common. That's why they had just 2 expression and we had 3 expression. I mean 3 terms. So yeah, you got the idea. You are being really active. I love that. Okay, What should we do for this one? Can you also suggest for this one? Okay, so what's the approach for this problem, guys? Think and let me know your opinion. Split the numerator. Split the numerator into what exactly? Split the numerator and rewrite. Oh, sorry, split the numerator and rewrite x. Okay, yeah, I can make numerator as x squared minus 2x plus 1, right? And then after that, what? And rewrite. Okay, split the numerator and rewrite. Wait, I can. Okay, let me write what you guys said, right? Okay, so I can write the numerator as x squared plus 1 minus 2x, right? Now, after this, what? Now, x squared plus 1 is same in both numerator and denominator. Yes, I also saw that. Okay, so maybe now then you might be thinking to write it like this: 2e to the power x minus 2e to the power x minus 2x. Is that what you guys thinking? Yeah. And like, how will this be helpful? Is it what you think? Yeah. You know, how will this be helpful? So I can write 1 minus 2 times e to the power x plus x, yeah, by 2e to the power x plus x squared plus 1 dx. Oh, this is really good, guys. This is really good, guys. Do you guys see why this is really good? Because you guys said it to me. Yes, okay, you guys say it. Because you guys said it to me, so of course you would say it. Okay, the good thing is, now I can write this as integral of 1 dx minus integral of 2e to the power x plus 2x divided by 2e to the power x plus x squared plus 1 dx. Yes, we have seen the dx in the numerator, exactly. Now if you let y as 2e to the power x plus, anybody from class 12 JS friend, maybe there are some guys, x squared plus 1, then du is 2e to the power x plus 2x dx, right? So now this thing is just x minus integral of du by u, right? So this is x minus ln of u plus c, and then u in this case is just 2e to the power x plus x squared plus 1 plus c, right? Oh, you did. Oh, wow. You are in IIT Delhi. Yeah, that's really good. Okay. And so, yeah, I think this is the answer, right? So let's see. Let's check the answer. X minus ln of 2e to the power x plus x squared plus 1. Yeah, x minus ln of 2e to the power x plus x squared plus 1. Okay, so we are done with this. Let's go to the next problem now. So we have made it to the half, and we are in the 11th problem now. This problem seems to be really interesting. We have max function, and yeah. So I think if we plot it, that will be helpful. Usually if there's max function, I try to plot it. Okay, so let's see. So let me try to plot this graph. this thing. Square root of 1 minus x square minus half. Okay. So first of all, we know that the square root of 1 minus x square. Yeah, exactly, use graphs. Yeah, that's what I'm going to do. If we plot 1 minus x square, we know that it's going to be this thing over here, right? It's going to be a part of the circle. Yeah. And yeah, square root of 1. And also, if for negative x as well, this is going to be a part of the circle, right? But in our case, this is shifted by minus half. So that means instead of the vertex being at 1, the vertex will be at half, right? So let's draw that again. And also, yeah, so if the vertex will be at half, let's see where it cuts in the x-intercept though. So basically, if I let this 0, half as square root of 1 minus x square, so for it to be 0, we need to have 1/4 as 1 minus x square as 3/4, x as root 3 over 2. Okay, so that means it minus root 3 over 2 plus root 3 over 2, that's where this circle passes from, right? Okay, and this is half, and this is a part of the circle, and this circle might complete over here. Its center will be at minus half, right? Okay, but the thing is, our function, yeah, quarter circle, exactly. Okay, but the thing is, our function is like whatever is maximum, right? Between. Bye guys, I need to go for class. Namaste. Okay, yeah, thank you so much for being here till now. You really gave some good suggestions. Thank you so much. Okay, so our function is maximum of these two things, right? So it can never be negative, because if this thing is negative, then we have 0 over here, so maximum will be 0. So we just need to look at the maximum function, right? So the maximum curve will be something like this. So over here from -1, so over here from -1 to 1, because this other curve is going down, so we will just look at 0 over here. Over here we will look at this curve, because that's more positive. Over here we will look at this curve. So we need to integrate on this region. So essentially, we just need to find this area. Okay, we just need to find this area. Okay, now how do we find that area? I think that is also gonna be something challenging, right? Yeah, so we will just do the integral. Let me just go with the integral approach. I think that will be more fine. So essentially, I just have to integrate from should I go with integral or no? Actually, wait, let me not go with integral. Should I go with integral, or I have some other ideas? Do you guys have any ideas to get the answer without doing the integral? Because I know the area of the half circle is, in this case, guys, let's go with the integral. Let's not think a lot. Okay, so from minus root 3 over 2 to root 3 over 2 square root of 1 minus x square minus half dx, right? And then over here, okay, because this is an even function, so I can write this as 2 times integral from minus root 3 over 2 to root 3 over 2 square root of 1 minus x square, right? And then there's this minus half. So what I can essentially do is, for that minus, I can just integrate it. So half times that will be root 3 if I just integrate it right now. So this will be 2 times from minus root 3 over 2 to root 3 over 2 of square root of 1 minus x squared dx, right? And then this is just minus root 3 over 2. Okay, I just integrated the second part. So half times, yeah. Okay, now let me do the integral. I can do the integral by substitution. I can just substitute x as sine theta, right? If I do that, this will be an integral from, okay, well, let me do cos theta. Let me do cos theta. And this will be an integral from, no, let me do sine theta. Then this will be an integral from minus pi over 3 to pi over 3, right? Yeah, because sine 60 is root 3 over 2. And this is gonna be cos theta, and then dx is gonna be also be cos theta d theta, right? Yeah, minus root 3 over 2. So integral from minus pi over 3 to pi over 3 of 2 cos square theta d theta minus root 3 over 2. So this is from minus pi over 3 to pi over 3. So this is 1 plus cos 2 theta d theta minus root 3 over 2. So this is theta plus sine 2 theta over 2 from minus pi over 3 to pi over 3 minus root 3 over 2. So this is just 2 pi over 3 plus half, wow, and sine of 2 pi over 3 is again just pi over 3, so root 3 over 2, and then that's minus root 3 over 2. So this just goes to 0, right? Is that it? But why would that go to 0? Because that comes from cosine, and which is even function, that should not really go to 0. Okay, so sine of 2 pi over 3 is just sine of pi over 3, right? Because cos of pi minus pi over 3, sorry, sine of pi minus pi over 3 is the sine pi over 3. Yeah. Oh wait, so this is plus actually. So minus root 3 over 2. So this is 2 pi over 3 plus, now this is, what the, now this is root 3 over 2 minus root 3 over 2. How is that cancelled? That should not happen, guys. Did I do any mistake over here? Okay, I just need to integrate that from minus root 3 over 2. And that is minus root 3 over 2, right? The intersection, because I just need to let this 0. So half is equals to square root of 1 minus x square. 1/4 is equals to 1 minus x square. X square is 3/4. X is root 3 over 2, yeah. So I first separated that. Yeah, that looks good to me. And then I made a substitution. That also looks good to me. And then I use the trig formula. The answer. And then I get the answer as 2 pi over 3. Which does not look correct. Guys, do you guys have any idea what could have gone wrong? Please, if you guys know where I went wrong, I would appreciate any suggestions. Okay, yeah, so this goes from minus root 3 over 2 to root 3 over 2. And then Anyone, guys? Anyone? Um, hmm, hmm, hmm. Okay, let me look at it carefully. Oh, I see. I don't need to keep in 2 over here because I still have the same limits of integration. Damn. So let me write half over here. I'm sorry, guys. I'm sorry for that blunder. And let me write a half over here. I'm sorry, guys. This is a blunder. This is a big blunder. Okay. And so this is a half of 2 pi over 3 plus half times it was root 3 over 2 plus root 3 over 2, right? Yeah. Okay. Now I get the expected answer. So this is pi over 3 plus root 3 over 4 minus root 3 over 2. So this is pi over 3 minus root 3 over 4. Is that the answer? Yes. Finally we get the answer, guys. I'm sorry for the delay, guys, but we are there. Okay, guys, let's go ahead. Did that make sense? If any one of you is here, if that made sense, we can go ahead, right? Any of you here? Should we go ahead? I mean, it wasn't a big deal. I just needed to find the area and I was messing up with the integral. I just had an extra factor of 2. That's all was there to this. Let's go to next problem, right? Because we got the answer correct. Yeah. So this was 10th problem. Let's go to 11th problem now. Oh, this was 11th problem. Let's go to 12th problem. Let's go to 12th problem. Copy. Let's go to 12th problem. Allow best. Okay, guys, so if any one of you is here, can you guys suggest me how to do this one? Because this looks really difficult to me. I don't know. It could be hard, it could be easy, it could be anything. Do you guys have any ideas on this problem? Let me wait 1 minute for ideas from you guys. Yeah. Any ideas, guys, on this problem? How should I approach it? I do have some ideas, but I want to go with your ideas first, if you guys have any ideas on this problem. It repeats, so denote a part of the radical as a variable. Yes, I was also gonna go with that thing. So let's say if we write this expression as y notice that the inside thing also same thing, because it's going to infinity. So essentially this thing is also y, right? So I can write it as y is equals to square root of x square plus x plus that is also y. So this becomes quadratic equation. Y square is equals to x square plus x plus y. So I just need to solve for y from here. So y square minus 1 minus x square plus x is equals to 0. So that means we have y is equals to minus b plus minus square root of b square minus 4ac over 2a. Here a is 1, b is negative 1, c is negative of x square plus x. So y is minus b, and I will take plus because the whole thing is positive, so I need a positive answer. So plus, and then b square is 1 minus 4a is 1, c is minus x square plus x, so this becomes plus x square plus x by 2 into a is 1. So we get the expression for y. 1 plus square root of 4x square plus 4x plus 1 by 2. Okay, so this thing over here is actually 1 plus square root of 4x square plus 4x plus 1 over 2. I can actually simplify this because the expression over there, it's just 2x plus 1 whole square over 2. So this is 1 plus 2x plus 1 divided by 2. So this is 2x plus 2 divided by 2. So this is x plus 1, right? This was a very nice simplification, guys. X plus 1. Who would have thought that this whole thing is just x plus 1? Funny. Okay, so integral from 0 to 1 of x plus 1 dx. Now this is just x square by 2 plus x from 0 to 1. So that's just half plus 1 minus 0 plus 0, which is just 3 over 2, which is exactly what the answer is over here. So this was an easy problem, and thank you for suggesting the idea. And yeah, let's go to the next one. This made sense, right? This was just letting a variable to the expression, and we get a quadratic equation, and we solve for y, and we simplify the expression, and we just substitute the expression for y, and we integrate it. That's all. So let's go to the next problem. Should we go to the next problem, or do you guys wanna comment anything? Do you guys wanna ask anything? I think it's pretty easy. Yeah, let's go to the next one. Problem 13. Woo! This one looks terrible. This one looks really complicated, guys. This one looks really complicated. Guys, let's first think, guys. Let's not do it immediately. Let's first analyze it, and then we'll do it. Okay, we have cos to the power 5, and then 10 cos cube x. Okay, sine square x plus 5 cos x sine to the power 4x. How should we do it? From the answer, I can guess that the whole integrand is just cos of 5x, right? I can guess that. But we don't really know that immediately. How do we know that this whole thing is just cosine of 5x? We don't know that. Yeah, sine square is 1 minus cosine square. And how will you use that? Yeah, I mean we can plug that, so everything just becomes cosine. Yeah, that's a good idea. And then when everything becomes cosine, what do we do after that? Maybe Yeah, let's go with your idea. Let's just make everything cosine and see if we can do anything. I think that would also be something I would like to do. Okay, let's just go with your idea. Okay, let's just plug everything. So this whole thing should actually be cosine 5x from the answer, but we don't really know that. Okay, cos to the power 5x minus 10 cos cube x. So this is 1 minus cosine square x plus 5 cos x, and then that is 1 minus cosine square x whole square, right? And then dx. So this is cosine to the power 5x minus 10 cos cube x plus 10 cos to the power 5x plus 5 cos x, 1 minus 2 cos square x plus cos to the power 4x, whole thing dx. Okay, so cos to the power 5x minus 10 cos cube x plus 10 cos to the power 5x wait You know what, guys? Actually, from this expression, we can directly know. You know why? Yeah, I don't think we need to go. We can actually know it from this expression itself. And the reason I say that is, guys, let's not go with this, Abros. I have something in mind. Yeah, okay. Let's not go with this. This is because this is just gonna be complicated, and I don't think. Do you have any solid reason why you wanna go with this? If you have some reason, I can go with this. Otherwise, I have something in mind. Yeah. I will tell you my idea, okay? It was just the first idea. Yeah, exactly. It was, yeah. That also came to my mind. But over here, notice that for cos x to the power I sin x, if you take the fifth power, it's the same thing, like cosine to the power 5x, right? And now the second thing will just be like 5, which is 5. This is, I think you guys know that this is 5 choose 2, this is 5 choose 4, right? And this is over here is 5 choose 1, sorry, 5 choose 0. Just the number 1 is 5 choose 0, right? So this is 5 choose 0 cosine to the power 5, and then 5 choose 1, we will have I cosine to the power 4x sin x, right? Plus 5 choose 2, we will have minus 1 over here, cos cube x sine square x. The fact that these were binomial coefficient, right? And then the power was also like in the decreasing order of 5, 3, 1, and from 0, 2 to 4. That was what, exactly. That was what gave me the idea, And then plus 5 choose 3, now this will be minus I cosine square x sine cube x plus 5 choose 4, this will be 1 cos x sine to the power 4x plus 5 choose 5, this is I sine to the power 5x, right? So over here, we know that this expression over here will also be equal to cosine 5x plus I sine 5x, right? This is from the de Moivre's formula or someone, I forgot the name, probably de Moivre's, yeah. So now if we just equate the real part from both expression. Equate real part. We have cosine of 5x as, yep, Moivre, yeah. So cosine of 5x as cos to the power 5x, and then minus 10 cos cube x sine square x, and then plus 5 cos x sine to the power 4x. So yeah, when you notice the binomial coefficient and the like decreasing nature of power by the same like number and increasing by same number, you can probably guess that it's a binomial expansion, and yes, it was. And then yeah, so that means because that's cos 5x, so we have integral of cosine 5x dx. So this is sine of 5x over 5 plus c, and that's the answer, guys. And this was actually a beautiful problem, and I think I also learned something new, like yeah, like how to see like the, you know, like sine 5x, cos 5x, sine 6x, how to see the expressions now. Yeah, I think this was a good learning for all of us, I guess. Yeah, let's go ahead. This was a good problem. Let's go ahead. Oh yeah, okay. Low power mode. I need to charge. Look at problem 14 and think of some good ideas for that problem, guys. What do you think will be helpful to solve the problem? Something like that. Think of some good ideas for problem 14 and let me know. Until then, I will charge my iPad. Yeah. Is it charging? No. Yes, it's charging now. Okay, good. Okay, yeah. Let's go with 14 now. U substitution. Yes, I think that's what I would go with as well. U substitution. So I think you will substitute u for root x, right? And the fact that today chat is very active and people are actively giving ideas, I really like that. So u is root x. So you will have, should I just substitute root x as u or the whole tan x thing? I think I should do for whole thing. Yeah. Tan arctan square. Yeah, I think I should do for the whole arctan thing. That would be much better. Okay. So and then I will have, if I do that, I will have tan u as root x, right? And then I will have x as tan square u. So x will just be 2 tan u 2 tan u times sec square u. Wait, is that helpful? Probably, yeah. I hope so. Guys, is that what you mean? Like, do you think that's helpful? Yeah, I think it's helpful. Yeah. Okay. Well, let's go with the. I think it's helpful. Yeah, I think it's helpful. Dx is equals to 2 tan u times sec squared u. Yeah. So yeah, let's go with this. Should we go with this? I don't have a good feeling about it though. But guys, you mean like u substitution for arctan of root x or just u of root x? I don't have good feeling about this. Let's go with u of root x. So then I will have u square is equals to x, 2u du is equals to dx, right? Yeah, let's go with u. Okay, and so this is tan inverse of u, and then dx is 2u du, right? So then, so this is 2 times tan inverse u with u du. Now this will be tan inverse u, and the integral of u is u square by 2 minus integral of its derivative is 1 plus u square by 2. Yeah, it works well now. So now this is just u square tan inverse u minus u square by 1 plus u square du, right? I multiplied by 2. So u square tan inverse u, I can write this as 1 plus u square minus 1 by 1 plus u square du. So this is u square tan inverse u minus 1 by 1 plus u square du. So this is u square tan inverse u minus u plus tan inverse u plus c. And since u is root x, so this is x tan inverse root x minus root x plus tan inverse root x plus c. And if you take tan inverse root x common, this is x plus 1 minus root x plus c. Yes, and then we can try and, yes, exactly. Then we can try integration by parts and see if 2 appears. Yeah. I mean, yeah, if you just differentiate this, it simplifies, right? So yeah, that was a good idea. And then yeah, this is the answer now. So tan inverse root x with x plus 1 minus root x. Yeah. To summarize, we first made the u substitution, so this is not a part of it. So we first made a u substitution, and then we simplified this a little bit, and then used integration by parts, and then we had tan inverse u to be differentiated, which is what made the integral easier later on. And that was an easy integral, so we got the answer. Yeah. This was an easy one, right? This wasn't too hard. Should we go to the next problem now? Or do you have anything to add to it? Let's go to the next problem, I guess. This was a good exercise. Yeah? Let's go to problem 15. Let's go to problem 15. Oh, this seems to be a really terrible problem, bro. I don't know if we'll be able to do it or not. Let's see. Let me drink some water before I do this. Guys, look at this problem, guys. Look at this problem. Okay. This looks like a terrible problem to me. I think we should do all of these integrals separately, one by one. Okay. The first thing I notice is that whenever you take a fractional part, this thing is... Okay, let me just... What are the brackets? Oh, okay, let me tell you about the brackets. Okay, so first of all, this is called fractional part function. Fractional part function. This is called floor function. And this is called ceiling function. Okay. So now the fractional part of 1.28 is just 0.28, just the fractional part. the fractional part of 5/4 is 1/4, because this is 1.25, so this is just 0.25. Okay, and the floor function of 1.28 is 1. The floor function is, you just round it down. Even for 6/4, the floor function will just be 1. You just round it down. And for ceiling function, you round it up. This will be 2. Even for 1.28, the ceiling function will be 2. Is that clear what these things are? Yeah. Okay. Now something interesting is, I think these two should be pretty easy, because this fractional part is always greater than or equals to 0 and less than 1. Okay, because like if you have 1, the fractional part is just 0. If you have 1.1, it's just 0.1. So because it's fractional part, it's always less than 1, right? So that means because it's always between 0 and less than 1, if you take its floor function, that should always be 0, right? Because it's like always less than 1. So like if you just take floor, that should be 0. Yeah. And then over here, for this integral, for the purpose of this integral, now, but like for the ceiling, if you take the ceiling, so this thing should always be 1. No, it should not really always be 1 actually, because like if x is, okay, so this should be 1 if x is not an integer, but it should be 0 if x is an integer. Or I can write natural number. Do you see why? Because like let's say if x is 1.5, then floor is 0.5, and then ceiling will be 1, right? Not if it's not natural number. But like if it's natural number, let's say if x is 5, the floor is 0, and ceiling of 0 is just 0. You see? The ceiling of 0 is just 0. So that's why, so this thing is 1 if x is not natural number, and 0 if x is natural number. So we can easily do these two integrals then. Like this integral from 0 to 1000, and we told that thing is always 0. So 0 dx, that's just 0, right? And for this one, so this just goes to 0. Now for this one, 0 to 1000 of ceiling of x, ceiling of this thing. So what we can do is we can like break these integrals into like from 0 to 1, right? And then from 1 to 2 and so on. And the reason I want to do this is, and from like 999 to 1000, okay? And the reason I want to do this is like, so this integral, while doing the integral, x is strictly between 0 and 1. I can just assume that. And so in that case, it's always 1, right? So in that case, it's always 1. So this is just integral from 0 to 1 of 1 dx. Another is also from integral from 1 to 2 of 1 dx. So essentially, for the purpose of integral, it's always 1. From 2 to 3. Yeah, for the purpose of integral, it's always 1. Okay. Yeah. So this is just 1 minus 0, 1. This is 2 minus 1, 1. So we just add 1. how many times? 1000 times. So this is just 1000. Okay, so we see that this one is just 0 and this one is just 1000. Okay, now let's go with others. Let's go one by one for all of them. Okay, so what about, okay, let me copy this problem again because it's already so messy. Let me copy this problem again. Okay, so till now we know that this thing is 0 and this thing contributes 1000, right? Okay, so what about, let's go with these two things now. Okay, yeah. Oh wait, we can also do these two easily. Okay, if we take fractional part of the floor, because this floor is always an integer and fractional part of a natural number should be 0, right? Because there's no fractional part natural number. So this thing is also just 0. It's always 0. So the integral is 0. And this thing is always 0. So the integral is 0. Because like fractional part of natural number is 0. The first two are the only one that matter. Exactly, yes. So first two are the only one that matter, okay? Okay, let's see this now. So, no, actually let's see this first. So I already told you that, so if you have, let's say, let's go with the approach we did earlier, right? I showed you how you can break this into sum, right? So you can break this as sum from n equals to 0 to, or from n equals to 1 to 1000, and you can go as integrals from n minus 1 to n, right? So this is from 0 to 1, and then 1 to 2, and then lastly from 999 to 1000. And then this will just be, if you take floor, this will be n minus 1, right? If you just take the floor function, it rounds down, and then in this range from n minus 1 to n, in this range, if you round down, that should be n minus 1 dx, right? And now even if you take ceiling, even if you take ceiling of natural number, that's just a natural number. It doesn't change. I mean, if you take ceiling of x and x belongs to a natural number, then that's just x. Okay, yeah. So because of that, even if you take ceiling, it will still be n minus 1. Okay, n minus 1 to n, and this is still n minus 1. Okay, now because this is constant, I can just take it outside the integral. And if I take the integral, that's just x, and if I evaluate it, that will just be 1. Okay, so now I need to do this sum, which is n minus 1. So this will be n into n. Okay, so from 1 to 1000. So for n, that will be 1000 into 1001 by 2, right? Minus, and for 1, yeah, it will just be 1000. Okay, so this is 1000 into 1001 minus 2 into 1000 by 2. So this is 1000, 1001 minus 2 over 2. So this is 1000 minus 999 by 2. And I will keep it as it is for now, right? Okay, so we have done this. Now let's do the other part. So we did for ceiling of the floor. Now let's do for the floor of the ceiling. So 0 to 1000, floor of the ceiling. Okay, we'll do the same approach. We will break this as sum from n equals to 1 to 1000, and the integral from n minus 1 to n. So in this case, if we take the ceiling, this should be n, right? Unlike earlier where it was n minus 1, in this case it will be 1 because we are taking ceiling. So sum from n equals to 1 to 1000, and this is just n because that's an integer, and for integer the ceiling or floor doesn't really do anything. Now if we integrate this, that will just be n. That we can take n as a constant, we can take it outside, and if we evaluate the integral, that's just 1, and this is 1000 into 1001 over 2, right? Okay, that's good. So we have these two. So now there's 0. We saw that this thing is 1000 into 999 over 2. This thing is 1000 into 1001 over 2. So let's add them all up. If we add them all up, let's do it here. So what do we get? If we add the first two terms, we get 1000 into 2000 over 2. So that's just 1000 into 1000, which is 1000000, right? And we have one more 1000 to add from here. If we add that 1000, we get 1001000, which is the answer. Do you guys see it? It was a very long problem. We needed a lot of things, but it was doable. Yeah? Okay, this was a very good problem, to be honest. Did you like it? Did you enjoy this problem? I think it's a really good problem. I mean, it did, yeah, it's simplified. Yeah, exactly. It simplified nicely, and it just involved the concepts and ideas, It was a really good problem. It simplified so good. Let's go with problem. Let's go with the next problem. Ooh. This problem also looks good. Okay, I will give some time to you guys to recommend me the ideas. Meanwhile, I'll just have some water. Okay, so what should I really do? Okay, let me first try to write all of them in terms of sine and cos, okay? That's the first thing you would do, right? If I do that, it will be cos x over sine x. And then again, for cot, cos over sine. For sine, for tan, sine over cos. For cosec, 1 over sine. For sec, cos over 1. So this is just cosine square x divided by sine square x. So that is just cot square x dx. And we know, can we not just simplify the expression into square root? Yeah, we could have done that. Wait, we could have... I don't know if that's really the right expression because I'm getting something different now. But yeah, we could have done something like that, yeah. Definitely, we could have just reduced it to tan and cot instead of sine and cos. I just thought of doing it this way. And then we know that cosec square x minus cot square x is equals to 1. So cosec square x minus 1 is cot square x, right? So this becomes cosec square x minus 1 dx. And we know that the derivative of the cot x is minus cosec square x, right? So the integral of cosec square x should be minus cot x minus integral of 1 is x plus c. So this is also really easy actually. Yeah. This wasn't bad. Even though it did look bad, but it wasn't bad at all. Minus x minus cot x plus c, yeah. Yeah, this was a fine problem. This wasn't a bad one. Yeah. Should we go to the next problem? I think we should. Problem. Oh, 17 looks good. 17 actually looks good. 17 actually looks good. I think we will love it. Let's go with 17. Okay. So guys, recommend me your ideas. I don't have anything in mind right now. How would we do this? I really don't know what to do. Hi, sir. Hi. We are doing problems from MIT Integration B 126 regular season, and I'm just waiting for you guys to give me some ideas to try so that I can try, and we will see if that works out or not. Yeah. It looks like a substitution should have. Yeah, exactly. Do you guys? Yeah, exactly. That's what I think we should be doing over here. Do you guys see that? Okay, I do see something. Do you guys see that the denominator is probably a transformation of the earth function derivative? Okay, probably it is. But like that is too complex. Like, this whole thing is a 30-minute exam. Like, and we already took it more than 2 hours. And if you go into that, the earth function, it will be more complex. I don't think they want you to use earth function. I see something here actually. Yeah, that's what I was thinking, using King's rule. Or that's what I was thinking. Or instead of using King's rule, it's the same thing. We can just make a substitution u is equals to minus x. And if we do that, notice that, okay, the limits of integral, first of all, becomes infinity to minus infinity, right? But then again, here you will have minus du, which will again reflect the limits of integral. And then because of this minus sign, the limits of integral will again be infinity to minus infinity to infinity, right? And the changes over here is we will have minus x squared by 1 plus e to the power 2 times minus x. Yeah? So this is equal to the original integral. Okay, and this is also King's rule. And this is King's rule. The reason is the King's rule says that, okay, I will explain in a minute. So this is e to the power minus x squared by 1 plus e to the power minus 2x. Oh, this should have been minus u. Minus u. Minus u. Minus u. Minus u squared to the power minus 2u du. I can again write this in terms of x. e to the power minus x square. It doesn't matter what variable I use over here. Okay, and yeah, so this is just use substitution, and also this is King's rule. And the reason it's King's rule is the following. Yeah, now you can add. Yeah, that's exactly the thing. Yeah, we are gonna add it now. Yeah, that's what I'm gonna do. But let me just show how it's a King's rule. King's rule says that integral from a to b of f of x dx is integral from a to b of f of a plus b minus x dx. And you can see that that's what exactly happening over here. Because over here, because domain is symmetric, a plus b is 0, and that's why the integral from a to b of f of x dx is f of minus x dx, because the domain is symmetric. Okay, so now we know that integral from minus infinity to infinity of e to the power minus x square 1 plus e to the power 2x dx, this is what we want, and we know that this is also equals to minus infinity to infinity of e to the power minus x square 1 plus e to the power minus 2x dx, right? Now you can take now you can multiply both numerator and denominator by e to the power minus 2x, e to the power 2x, and that makes it e to the power 2x plus 1 dx. Now if you add these two integrals, we have 2I is equals to minus infinity to infinity e to the power minus x square 1 plus e to the power 2x divided by 1 plus e to the power 2x, and that is a very nice cancellation, guys. So this is 2I is equals to minus infinity to infinity of e to the power minus x squared dx, and we know that this is just root pi. This is the famous Gaussian integral. So I is root pi over 2. And this was a beautiful solution thanks to Daxia. I think it's Daxia. Yeah, for suggesting the King's rule. Yeah, root pi over 2. This was a beautiful problem, right? Like, we had to notice that we can actually add a different version of this integral to simplify it. And this is actually a really popular technique, so that's why like people might see it immediately because it's really popular. Yeah. This was a good one. Do you guys have any doubts? Anything that you haven't understood? Or should we go to the next problem? I'm from India and preparing for Yayyy exam. Yeah. I think Yayyy exam is really competitive and it takes a lot of effort. And I think you are probably preparing well. I hope so, and I hope your exam also goes well whenever it is. Yeah. Let's go to problem 18. And I think you are really good at integration. Like, yeah, I can see that. Okay, let's go to 18. Copy. Okay, now how should we go with this problem? Okay, problem 18. Okay, give me ideas. How will you approach this problem? You know what I would do? I would just try to integrate by parts the first thing and see what I would get. Because it feels like if I integrate 1 over x squared, I would get something similar to this. 1 over x, and then again over here also something similar. I would do that. I would just integrate the first thing. Let's do it. So if I just integrate the first thing, first of all I will have sine square x as it is, and the integral of 1 by x square is minus 1 over x, right? Minus, and then derivative of sine square x is 2 sine x cos x. Integral of 1 over x square is yes by parts, yeah. So minus 1 over x, right? And the last integral, this expression will be as it is. So minus integral of sine 2x over x dx. So this is minus sine square x over x, and that is plus sine 2x over x dx, and that is minus sine 2x over x dx. And yeah, that nicely cancels out, and we get the answer minus sine square x over x plus c. Yeah. Yes, that is the answer. Minus sine square x by x plus c. This was an easy problem. This was a very easy problem actually. This was the next one. Woo! Next is challenging. Next is really challenging. Next is really challenging. I definitely need your help, Daksha, with this problem. Who is giving Z? Oh, tomorrow is Yayyy Men's. Good luck, guys. Good luck for Yayyy Men's. I hope you guys do well. Okay, suggest me some ideas for this one. I do have an idea actually. Okay, what do you think? I do have an idea, but like I want to go with your idea. Do you guys have anything in mind? Yes, substitute. Yeah, exactly. If I substitute u as log of x, my du will just be 1 over, yes, 1 over log x, 1 over x dx, right? So that's a really good thing because with that, so it will just be u and then log u and then du. Yes, and now we can do it easily. So it's just u log u du. Now we can do integration by parts. So log u with u square by 2 minus integral of 1 over u with u square by 2 du, right? Yeah, I just differentiated log u and integrated u. So now this is log u square by 2 minus, now this is u by 2, so u square by 4 plus c, and u is log of x, so log of x whole square with 1 over 4 minus sign plus log of x, right? And then with log of x whole square over 2. Yeah, that should be the answer. Let's see. Okay, so up here they took 1 over 4 log of x whole square common. That means they will have minus 1 over here, and they will have 2 times log of x. Yeah, and I think that's what they have. Yeah, so we are basically correct. Yeah, that's the answer. Yeah, and thank you to Jivhardi. I don't know how to pronounce your name. Jivhardi, something like that. But yeah, thank you so much for the idea. Next thing is this problem. This is the last problem, guys. We actually solved all 20 problems live without preparation, guys. That's really good. Definitely we took a lot of time, but we were able to do all of it. I think we will be able to do this one as well. Yeah. Okay, guys. Time for ideas now. Let's think. And if you have any ideas, tell it to me. This one definitely seems a bit challenging, I guess. I don't know, but I can again use King's rule, but that will only change one term, make it sin square x. Oh, wait. I see the solution, guys. I see the solution. It's again based on King's rule, guys. Do you see it? Do you see it, guys? I see the solution. Do you see it? It's very beautiful, guys. It's so beautiful. Guys, it's best. Yes, it's symmetrical. Yes, that's true, guys. Okay, so I told you earlier that from King's rule, this thing is equal to f of a plus b minus x dx, right? If you do the same thing, this integral I over here, cos square pi over 2, cos square pi over 2, cos square x dx. This is also equal to 0 to pi over 2 cos square pi over 2 cos square pi over 2 cos square of pi over 2 minus x, right? I can do this from King's rule. And now notice that this thing becomes cos square pi over 2 cos square pi over 2. Now this will be sin square x. Yeah. Okay. Now what I can do is I know that sin square x is 1 minus cos square x, right? So this is pi by 2 minus pi by 2 sin square x. I just use the, pi by 2, yeah, so pi by 2 minus pi by 2 cos square x, right? I just use the fact that sin square x is 1 minus cos square x. Yeah, so that is, this is cos square x pi by 2 cos, this is now sin square of pi by 2 cos square x. Yeah. Okay, I can again now use the same thing, the fact that sin square is 1 minus cos square. So this is pi by 2 minus pi by 2 cos square of pi by 2 cos square x dx. So this just becomes integral from 0 to pi over 2 of sin square pi over 2 cos square pi over 2 cos square x dx. Now I was also, okay, now I use this thing, but I was also cos square pi over 2 cos square pi over 2 cos square x dx, right? This thing was I initially, and now we have changed it to different thing. So both of them are our required integral. If we add them, that becomes 0 to pi over 2 sin square of some theta plus cos square of, it's the same theta, right? They're same. And we know that sin square theta plus cos square theta is 1. right? And that is just pi over 2. So I is just pi over 4. That's the answer. This was a really beautiful problem, to be honest. I would love to make a video on this sometime later. The last problem was beautiful. It ended up so well, bro. It ended up so well. And thank you to the guy who is still there, who was there with me from the beginning. Thank you for being with me the whole time. It was really fun solving problem with you. So we are done with problem 20 as well, and I think that's all the problems from okay, 19, 18. It feels really good to look back and see how much problems you have done, how much problems we have solved together. Okay, so that was the 20 problems from MIT Integration B 2026. So with that, we are basically done with all the problems from the website, and I think this was a qualifying round or regular season, right? And then regular season, I think today was the final round was today as well. They haven't uploaded the problems yet in the website, so whenever they have the final round problems, I will see if I can solve them, and if I can, I will try to make videos and upload it. And those are really good problems. So I will see if I can make videos, and if I can, I will make a video on the website. And you can also give a try to the problems yourself. MIT, just Google search MIT Integration B website, and you will see it. And you can give a try, give the solution, so that it will be helpful for me. Where can I find a book on integration techniques? There is actually a book by someone. Is first one? It's a 0. It's odd function over here, and because it's odd function and symmetric domain, that's just 0. You don't really need to do anything. But if it was 0 to pi over 2, definitely I would use beta function. Actually, a book online on ResearchGate by someone. You can actually use that book, or you can just do a lot of integrals. Let's say I made integral of previous integration B's. I have playlist for Nepal integration B's and things like that. So if you just do those problems, I think you will have the idea. That's what I'll probably sleep after this. But it was definitely a good time solving all these problems. And I also